Hello my friends, HM here, and in this video I'm going to talk about computers and data storage at the end of Moore's law. There's a lot of videos out on the internet on this topic, but none of them have figured out the obvious thing that data storage actually has a lot more transistors in them than chips made for computation. So the way I cover the topic, I'll of course include data storage. I've organized my video as a PowerPoint presentation where I have collected all the material that I have found during my research for my video. And there's a link below where you can find this PowerPoint presentation and download it if you like. However, before we start, I'd like to say that HM Experience is a video blog that focuses on anything that can importantly matter for whether the future of humanity will be better or worse. That means I talk a lot about developments in technology like this video, but also about global developments in politics and economics. With that said, let's get to it. So let's begin this presentation. As you can see, I've called it the state of computers and data storage at the end of Moore's law. To start, I think we should take the definition of Moore's law and just say what was it he said. By the way, Gordon Moore, that has the name of this law, he was a former CIO of Intel Computer. And back in 1965, he stated this law, which is not a law, it's rather an empirical observation or regularity that says that the number of transistors in a dense integrated circuit, that's a computer chip, doubles about every 2 years. And here we could say Moore's law is an observation and a projection of a historical trend rather than a law of physics. It is an empirical relationship that gains from experience in production. I may add that in 1965, Moore said that it would double every year. So transistors and circuits would double every year. And then he corrected that in 1975 and said it would double every second year. Okay, so what has this Moore's law got to do with the future of humanity? Well, the thing is that integrated circuits or computer chips for computing and for data storage, they are massively important for the future of humanity. They enable all aspects of modern life. Without these chips, we would simply not be able to progress our economies that much beyond the level we had in the 1960s. Because the thing is that nearly everything we produce, both in terms of physical goods and also in terms of services, information services, they use these integrated circuits or computer chips in one way or another. So therefore, how far humanity can progress economically and intellectually critically depends on further advances in making integrated circuits. We have also, why I say intellectually is that we become smarter the better computers we have, because it's a tool to enhance our understanding of the world and to control and manipulate the elements that are the world and that we need to have control over in order to create amazing new technology and machines that can help us in our lives. So that's why Moore's law matters, and that's why investigating when we can no longer squeeze more transistors into a circuit and also how advanced these circuits will be at the end of this progression matters. Okay, so let's start by looking at the evidence. Here I have found a graph that plots time on the x-axis and number of transistors on the y-axis, and then it has plotted these data for a lot of integrated circuits or ICs that have been developed over the years. And we can see here that we could actually fit a straight line through all these data points. And because we have a logarithmic scale on the y-axis, that means that we have a constant accelerating growth. It's an exponential growth and it's constant because it's a straight line we can fit here. Had it been curved downwards, then the growth would have been decelerating. And had it been slowed upwards, it would have been accelerating. So let's calculate the constant growth rate because it's a straight line. And we can do that by using this formula down here. And we have some data points that we need. For 1971, we had 5,000 transistors, and in 2019, we had 40 billion transistors, so quite an increase. And then we have 48 years in between, and that's all we need to calculate the growth rate. And we calculate it here, using this formula, and in percentage that's 40% per year. By the way, this video there will be a link where you can download the Excel spreadsheet that will have all these calculations inside, and where you can also, if you have other data, you can easily calculate growth rates for anything else just by using that Excel spreadsheet. So that might be something you'd like to download. Okay, Gore is talking about doubling every second year of transistor count. So let's see if that fits. So if we take these 40% and calculate the 2-year growth, then we can see it's 1.94. So that's almost exactly 2, as Gordon has predicted. It's almost a doubling every 2 years. And if you use this formula here for 10 years, you would see that it would have almost 30 doubled in 10 years. So we have a practically spot on here with Moore's law. Okay, let's move on to the next slide here. This slide here shows some state-of-the-art ICs or integrated circuits. I have collected them to show that not all circuits are created equal. They are quite different, and that matters for the rest of my presentation. So let's start by looking at this one, A15 Bionic by Apple. It's used in iPhone 13 Pro. It was created last year. It's a system on a chip, meaning they have integrated everything like processing unit, graphic unit, and memory on this chip. A lot of other stuff as well. It has 15 billion transistors. It has a transistor count per square millimeter of 138 millions. And it has a processing speed per watt of 0.18 trillion floating operations per second. And that's measured using a FP32 standard, which is a high precision calculation unit that was normally used to denote these teraflops speeds previously. Now we have shifted to another standard that has less precision because we are doing AI, but I'll come back to that. Okay, another chip here I'll show you is a more recent one. It is the M1 Ultra from Apple. It's from this year. It's also system on a chip, and it's made on 5 nanometer technology. It's a lot larger than this A15. As you can see, it's 868 square millimeter. So it's almost 8 times larger than this A15. So just because it's bigger, it will also have more transistors. Indeed, it has 114 billion transistors on this chip. And it's not made quite the same as this one A15 up here. It's actually a chip that has been made from 4 dies, and I'll come back to what that is. But let's move on to another well-known processor. It's not that well-known. This is a brand new one from NVIDIA. It's H100. The well-known is A100, but this H100 is the successor to A100 that is used everywhere for AI computing in supercomputers. But now it's this one, A100. It's brand new. I think it came out here in September. It has 80 billion transistors. It is almost as large as this one, the M1 Ultra by Apple, but it's made on 1 die, and it also uses a lot more electricity. It uses 700 watt. So it's actually slower in terms of teraflops per watt than this M1 Ultra by Apple. And you can see that here it has 0.096 teraflops per watt, whereas this Apple M1 had 0.35. And by the way, tera means 1,000 billion. That's a big number. It's a lot of calculations. It's a mind-blowingly big number. Most of us don't know or have any comprehension what a tera, what a trillion is. It's something you don't see a lot. But now it's becoming normal to measure stuff in trillions in computer speed. And then we have another chip, should be known now for anyone who follows Tesla, because this is the D1 from the Dojo supercomputer project that Tesla is running, and this is their chip. It has 50 billion transistors. It's smaller than this NVIDIA. It's 445 square millimeters. So it packs 77 million transistors per square millimeter, a little little less than the brand new H100. But it's fair to mention that H100 by NVIDIA is built on the very latest in processor technology. It's built on 4 nanometer technology, whereas the D1 from Tesla is built on 7 nanometer technology. So obviously Tesla will have another chip in the workings that will be based on this 4 nanometer technology that's faster and better, so they can squeeze more power out of it. A chip called Wafers Scale Engine 2 by Cerebras, and it's made for artificial intelligence operations. It's a unique chip because it's made from one die, and that die is the size of an entire wafer. Shortly, I'll explain a little bit more about that, but you can see the size of this chip is 46,222 square millimeters. So it's a gigantic chip. It has 2,600 billion transistors on this chip. So, every single study there is on Moore's law, they haven't considered that you could actually build a wafer scale chip like this. They have only considered these small chips that are used for processing of data. Okay, the last chip I want to talk about in this table is the VNAND 3D chip by Micron. It's a data storing chip, unlike the other chips or ICs that are mentioned above, that are all data processing chips. So this is a data storing chips. The unique thing about data storing chips is that they don't have thermal issues like data processing chips have. Data processing chips have to turn on and off their transistors, all of them almost all the time, like billions of times per second. But that means they generate a lot of heat. And that also means you can only make one layer of transistors on a die. If you put more layers on top, they will melt and burn down. But not with memory chips, where you only have to access the memory that is stored in some transistors occasionally, because it's a huge block and you only read a little bit of total memory in that chip. So there are really no heat issues when making memory chips, and that means you can stack them. And this specific chip has stacked 232 layers per die, and it has 16 dies that are then stacked on top of each other. Then that gives a total of 3,712 layers in one chip. And that means it has a mind-blowing 78,000 million transistors per square millimeter, way, way, way beyond the capacity, you could say, of these other computing circuits that are all below 150 million per square millimeter. And you can also see this chip has a massive 5,333 billion transistors on its chip, also much higher than the other chips and even higher than this wafer scale chip by Cerebras. So this table is simply to give you an understanding of how different the universe of chips or integrated circuits are. And also none of the other studies I've seen on Moore's law have actually included chips that were made on entire wafer, like this one from Cerebras, or any data storing chips that can be stacked. So I do that in this take on Moore's law. Okay, next slide. This slide is simply some sources for the previous table here. I've included it because you can download this entire presentation, and then it's a nice thing to have all these links so you can verify that I haven't made any errors, or you can get more information if you follow these links. I have a PhD, so I'm schooled in scientific methods, and making references to where you got your information from, that's a must. Okay, I want to give you some background information about how these integrated circuits are made. They start their life with something called Ignots, which are these huge thing here of pure silicon, a very pure kind of silicon. There's very little impurities in it. And it's a silicon crystal. The big one here is probably the biggest ones that we can actually build. They'll be 30 centimeters wide. And then these Ignots are then sliced up in thin layers or discs that are shown down here. And they are 1 millimeter thick when they are cut up. And then they are polished, so they'll get less than 1 millimeter thick. And when they are cut and polished, these discs are called wafers. So they go from Ignots to wafers. And then these wafers are used to actually produce the integrated circuits on top of. And that's done using photographic layering of material on top of these wafers. There is a fume of chemicals that are light sensitive. And when you light these wafers with a pattern of light that resembles the integrated circuit you want to fabricate, then these chemical vapors condenses along the features and small things that you want this circuit to build up of. And you do that thousands of times with different fumes and chemicals in order to build these integrated circuits up. And that's how it's done. Now, when you have this picture you can see here, you can almost see that there's a lot of small squares on it. And actually these are dies. They're called dies because then you cut this wafer up along these lines here. And what you get is a lot of small dies, like the one I'm showing over here. The one I'm showing over here is from Tesla. It's the D1 chip from Tesla's Dojo project. And basically it's a die that has been cut out of a much larger wafer. Okay, let's move on to the next slide. This slide here shows the relation between wafer size and die cuts. And also it shows that we started out making integrated circuits on some much smaller wafers that were only 1 inch in diameter, 25 millimeters. That was in the 1960s. And as time went by, we have used larger and larger wafers. And today we are still stuck on 300 millimeter wafers, but we already had those in 2002. And we haven't really further increased the size of these wafers, and the reason is that it's immensely complicated. The industry that manufactures integrated circuits is the most complex industry by far of any industry in the world. So to change anything in that production is just an enormous work in terms of all the other machinery you have to then adjust and change. So nobody is really interested in changing it because, we have a machine that works now. But in principle, you could make less costly chips or integrated circuits if you make them on an even bigger wafer. And we have proposed to go to the next step, which would be 450 millimeter, but it hasn't happened and it might not happen. In the future it will happen, eventually it will happen, because you want to have these cost savings. This table also shows you how many dies you can cut from a wafer, depending on how large it is. So from a 300 millimeter wafer, you can typically cut 660 dies. Now, not all dies are equally large, so it will also depend on, of course, how big your die will be. In this case, they have used 100 square millimeter die for an example. And down here we have the picture again about these wafers that will be cut. This is just a little background I thought would be interesting. The next slide here shows you something that has become relevant in the last few years for the manufacturing of integrated circuits. It's about that we have started to use so-called multi-die chips or chiplets. And to understand what that is, for instance, previously all chips were made on single dies, like this one over here, monolithic die with the M1 Max chip from Apple. That's similar to the A15 Bionic, if you can remember. That was a chip also from Apple that was used in iPhone 13 Pro that I just showed you slide 6 previously. But as the need for compute is getting larger, you can of course just make the chip larger, or you can start combining several smaller dies together to form a single chip. And that's what is happening a lot now in recent years. For instance, Apple's M1 Ultra is actually, it's called a chiplet. It has 4 dies that are connected with an I/O die, which is an input-output die that controls the information flows in and out of these separate die chips to form one unit or one integrated circuit. Of course, these are used in larger machines like laptops or notebooks, desktop computers that have more capacity to deal with heat than an iPhone, where you could say the maximum energy you can use is less than 10 watt. And that's why they only use one die there. But in desktop computers, they use more. Also, if you have been very attentive, You remember that I also presented a chip that was single die and that filled an entire wafer. You could of course ask yourself, why don't you just make a bigger die in order to make a more powerful chip instead of splitting it up in smaller dies and then combine those to form a single unit? Wouldn't that be more practical or easy? And the reason that the industry don't like to do that, in fact, no one have done it apart from one, is that whenever the die size increases, the probability of making an error manufacturing these dies will also increase proportionally with the die size, of course. So if you build an entire wafer with one big die, then the probability that there would be an error in that wafer scale die would be 100%. There will definitely be one error, and then there will be several errors somewhere on that die. And that would mean you would have to, if there's just a single error, a single transistor that isn't built correctly so it doesn't function, then you have to throw out everything you have built, and that will increase the cost. So the smaller the die you have, the less the probability that you'll have to throw out the chip because of an error on that die. That's why it has been very popular now to build more powerful chips, integrated circuits, simply by combining smaller dies together. But if you have been very attentive and can remember that I just in slide 6, I talked about a company, Cerebras, that are building a wafer scale die. So they do build one die the size of the entire wafer. And how do they do that? Because obviously it will have errors on it. And don't they have to throw it out then if it have errors on it? Well, they have, as the only one in the world, I don't know anyone else who are doing it that way, but they've developed a system where they split the chip they are building on that wafer scale. They split that into sectors, and when the circuit is manufactured, then they can run a program that determines which sectors have errors on them and which sectors don't have errors on them. And sectors on that wafer die that has errors on them will be shut down, and all the traffic information in and out will simply be rewired around these bad sectors so they're not used. And therefore they don't have to throw out the chip when it has been manufactured. There'll just be a small percentage of sectors that are bad, and they will be shut down, and it's not a problem for the way they built their chip. So that's why. Okay, let's move on to the next slide here. I wanted to show you that data storing chip that I talked about in slide 6 above, what kind of product that will end up in. There'll be a 2 terabyte micro SD card for mass market in 2023, where you can actually get that chip, because that micro SD card will have this chip from Micron in it. And it has these 16 dies on top of each other, each with 256 layers of transistors for memory storage. And it's actually no thicker than 0.8 millimeter at its thickest point. I'm just going to show you how small this is, because this is a micro SD card. Maybe I can get my camera here to focus on it. Yeah, now it focuses, great. And here from the side, it's very thin, 0.8 millimeter thin, and it contains 5,333 billion transistors. That's mind-blowing. That really is mind-blowing. Your iPhone 13 that has a computational chip in it only has 15 billion transistors in it, but these memory chips here, 5,333 billion transistors. That's insane. So I thought that was interesting, and you'd be able to buy this kind of micro SD cards for, I don't know, $400 on Amazon next year. Let's move on here to the next slide. So the king of transistor density is data storing ICs. It's not the compute ICs, obviously. But when Moore stated his Moore's law back in 1965 and 75, these data storing ICs didn't exist. But today they exist, and that's why we need to recalculate Moore's law using these data storing ICs as the endpoint in our calculation. So One endpoint here would be this state-of-the-art 2 terabit micro SD card with 5.3 trillion transistors. Goes into mass production in 2023. That's from the beginning of our period here. That was 1971. So it's 52 years, and now we have all we need to redo the calculation. Redo it using the same formula as previously, this one, and we get 50%. So there's an annual growth rate of 50%. Now, if you can remember, when we did it previously, we got 40% in growth rate. So now it's increased just 10% to 50%. And if we calculate the 2 years growth, then it's actually 2.224. That's still spot on with Moore's law. Now it's a little more than 2. Before it was a little less. As far as I remember, it was 1.9 or something. Now it's 2.22. So it doesn't really matter that we have a much larger count of transistors now with the inclusion of these data storing ICs, because it's spread over 52 years, so it doesn't appear to be much of an effect. It's still 2. But we can see if we calculate the same growth over 10 years, now we get, with this 50% growth per year, now we get a 54 doubling. Before, when we used 40% growth per year, we got a 27 times doubling. So here it matters. The longer period you consider with growth, the more important the difference will be. That's what characterizes exponential growth. That they doesn't matter so much in the short term, but they start to matter a lot when you consider multiple periods. Okay, so back to the question of when will Moore's law end. Moore's law will of course end when we can no longer shrink the size of transistors built on an IC. And obviously transistors cannot be smaller than the size of the atoms that they're made of. So we can reformulate the question to how big are the atoms used to make the transistors in an IC, and how many atoms do we need to actually make a functioning transistor, both currently and at the end of Moore's law. So let's take a look at how big the atoms are first. There's this table here I have made, and there's a good reference in Wikipedia about it that lists all the sizes of the atoms in the periodic table. But I only put up 3 here. It's silicon, and that has a size of 0.22 nanometer. That means we can stack about 5 of those atoms in 1 nanometer. Hydrogen is the smallest of all the atoms that exist, and we can actually stack 20 of those on a nanometer. But it's a gas. There won't be any gaseous hydrogen atoms in a transistor or an IC. So there will be molecules of some sort. And cesium is the largest of all the atoms. It's half a nanometer wide. So we can stack 2 of those on a nanometer. And then there's I found here at Quora.com, I found a guy, PhD, he seems like he knows what he's talking about, saying Dihong, and he said that actually all the elements that exist are used to make integrated circuits, apart from all the radioactive elements that would be plutonium and uranium. And then he lists a few here: lithium, neon, sodium, rubidium, iodine, and cesium. That was actually that one up there. They are not used. But everything else apparently is used to make these integrated circuits. But we know there will be between the smallest size of hydrogen and then the biggest here of cesium that's actually not used. So, and that's some sources I have here from this table. So you can, if you download the presentation, you can get these sources. Let's look at more context here about nanometers and transistor densities. I found another source here that lists some production technologies that some of the large chip making companies in the world have developed. Actually, IBM, I don't think they are making chips themselves. They are just developing technologies for producing chips. But TSMC is, I believe, the world's largest chip manufacturer or IC manufacturer, and followed by Intel and Samsung, who also manufactures ICs. And here you can see some of the technologies they're using. It's listed here with the oldest technologies first. 22 nanometers has been used by Intel to create transistor densities of 16.5 million transistors per square millimeter. But what we're interested in is perhaps the most recent chips. That would be 5 and 4 nanometer that are in actual production. We saw it with Apple in the previous slide. In that slide 6, we saw that iPhone are all using these chips that are made on this 5 to 4 nanometer technology that can simply structure elements on the integrated circuits that are 5 to 4 nanometer wide. But IBM apparently holds the record here, but that's in the laboratory. It's not in mass production yet, of 2 nanometers. So we know we can get to 2 nanometer, and they made you could say a test chip to prove that they can get to 333 million transistors per square millimeter. Let's move on to the next table. What is the smallest possible IC structures? I'd say from the previous slide, we saw that the atoms here range from 0.05 to half a nanometer. It's not because I know it for sure, but I'd say that 5 atoms side by side, that is the minimum we need. We cannot go below that. So if we assume that 5 atoms are needed, the problem with going smaller than 5 atoms is that all kind of weird quantum effects starts to happen. It's impossible to build something with a desired functionality in an integrated circuit. So I think 5 atoms is about as small as it can get. So we can multiply the lengths of these atoms that we saw previously. For instance, the hydrogen was 0.05 and multiply that with 5. Then we have a quarter of a nanometer, and the largest atom was 0.5. Multiply that with 5, then we get 2.5. So we get something in between a quarter of a nanometer and 2.5 nanometer as the absolute smallest way to organize components in an integrated circuit. And I'd say about 1 nanometer in average. I don't think we can build stuff on average with 1 nanometer precision on an integrated circuit. We cannot go below that. That I don't think is possible because atoms have the size they have, and that's why we can't go smaller. So then we have to figure out when will we reach this 1 nanometer tech, and we should also study if there's any regularity. As the year has gone by, our ability to produce steadily smaller stuff on these ICs has progressed. So is there a regularity for that? And that will be the next slide. Okay, so this is the next slide here. And we can see that we have a graph that plots the nanometer technology and the year that nanometer technology was introduced in the global market for IC production. And we can also see that you can fit a straight linear line here through these observation points from 1970 to 2019. And that means it's an exponential growth. And because it's slowed downwards, it's a negative exponential growth. And we know it's exponential because the y-axis here is logarithmic. And a straight line in a logarithmic graph, that's a constant exponential growth. So we can use the exact same formula as before. I've done it down here. And we can calculate that each year, on average, we can shrink the size of the features we can produce for any IC by minus 14.3%. And then I take this percentage and put it into an Excel spreadsheet where I say the first year is 2019 and we had then 7 nanometer. That's what we observe here. And then use this negative 14.3% growth to calculate what the nanometer technology would be in the subsequent years. And we can see we reach the 1 nanometer technology where I think Moore's law will be definitively dead because we can no longer shrink the size of the components we are putting on these ICs anymore when we reach that point, 1 nanometer on average for these structures on the IC. And that will be in 2031 to 2032. So that's about it. Okay, so in slide number 16 that I talked about before, we saw that IBM had announced in 2021 that they built this proof of concept circuit using 2 nanometer technology with a transistor density of 333 million transistors per square millimeter. To go from proof of concept to mass market production, that takes several years. So, and this nanometer law that we just derived predicts that it will take until 2027 to see mass market applications with 2 nanometer ICs inside. 2 nanometer ICs will probably be in 2027 in the iPhones and computers also from Apple and from Samsung and all the other big vendors. That nanometer law there also predicts that by 2031 we will see mass market ICs built on 1 nanometer technology. It's actually reasonable to expect that 1 nanometer mass market computational ICs that are made in 2031 will have a transistor density of about 1 billion transistors per square millimeter. And the reason I think that's reasonable is that you can fit 4 1 nanometer squares on each 2 nanometer square. So you just multiply those 333 million transistors that IBM got on their 2 nanometer tech, and that you multiply with 4, and then you subtract a little bit overhead, and then we get this round nice figure of 1 billion transistors per square millimeter by 2031. And also you should know that this 1 billion transistors per square millimeter is about 10x of what we got with new iPhones this year in 2022. So what can you do with 10x as many transistors? You can definitely make the iPhones 10 times faster than they are currently. So that's something to look forward to. But there's a thing that's very important, and that is that all we have talked about here for these ICs was actually the computational kind of ICs. The data storing ICs can be stacked, as I've also previously talked a little bit about. And Moore's law is definitely not dead in 2031 for data storing ICs. The reason that data storing ICs can be stacked, unlike those computational ICs, is that you only access memory in transistors very seldom. So when you read and write from a data storing IC, that's when you are actually accessing these transistors and have to open and shut them. And that will generate a little bit of heat, but you don't read the entire hard drive, so to speak, on the data storing IC. You only read a fraction of it. And that's why it doesn't generate a whole lot of energy. Whereas in a computational IC, you are turning transistors on and off constantly, like literally billions of times per second, all over the circuit. And that generates a lot of heat. In fact, if you can remember from slide 6 above, these computational ICs, they use between 0.1 and 0.8 watt per millimeter. That might not sound like a lot, but it actually is quite a lot, because it's between 10 and 80 watt in a square centimeter. A square centimeter is like what you have here in my fingernail here. That's a square centimeter. And it's something that is only a few nanometers thick. I think a human hair is like 20,000 nanometers. So it will be an extremely thin layer of transistors in a thumbnail area that has between 10 and 80 watt going into it. That's a lot. So it's no wonder they will burn off and self-destruct if you try to stack a computational IC. Okay, to estimate when Moore's law will end for data storing ICs, we can first note that at slide 6 and also 11 above, they showed that this state-of-the-art Micron-based micro SD cards, they'll be available in 2023, and they'll be using a 16 nanometer tech, and that implied single layer transistor density was 21 million transistors per square millimeter. So that's a lot less, that's a little bit odd, because why do data storing ICs use a more old, out of date, you could say, nanometer technology than the processing ICs? I'm not sure quite why, but my best guess is that there are further complications building data storing ICs that might mean that it will take longer to get the nanometer tech minimized for these circuits. But I think the most important, I don't believe that reason. I think the most important reason is that there's the most money in using the very, very latest nanometer tech for producing data processing ICs, because they go into computers and iPhones and so forth. And also we can actually store quite a lot of data even in these data storing ICs, even with the old tech. So demand for or the urge and pressure to increase performance on these data storing ICs is not as huge as it is for the data processing ICs. That's my explanation for it. But the fact is, they're only using 16 nanometer tech, and that means data storing ICs have a lot of potential to develop for much longer time than the data processing ICs that are already today at 5 nanometer and 4 nanometer. So if we assume 5 years between each 50% reduction in nanometer production, it will take about 20 years, 16 nanometer, 8 nanometer, 4, then 2, and then 1. That's 20 years if there are 5 years in between. So that will be from 2023 to 2043 before the data storing ICs reach that 1 nanometer limit with a transistor density of 1 billion per square millimeter. We can also use this nanometer law. That's a little more scientific than just assuming, probably takes 5 years to cut the components in a data storing ICs with 50%. And this nanometer law actually gave us until 2041 as the year that Moore's law will end for data storing ICs, which is really very close to this. It will be reduced by 50% every 5 years from now on. But we can also, I have made the graph, of course. This is a previous graph. We have this nanometer law minus 14.3%, and then we just take the Excel spreadsheet that can be downloaded, by the way, with all the data in it. We plot in 2023, 16 nanometer, and then we use this growth. It's just a negative growth rate to see when we'll hit 1 nanometer. We do that in 2041. So that's how that is. Now let's see if we can calculate how many transistors we can squeeze into a cubic millimeter at the end of Moore's law in 2043 or 41. The way I proceed here is that we know that Moore's law will max out with about 1 billion transistors per square millimeter, and that was in 2031, 32. So let's take the square root of 1 billion transistors on 1 millimeter, square millimeter. That'll give us 31,600. So we multiply that with itself, we get back to 1 billion. So that will give us 31,600 layers of transistors that we could potentially fit into a cubic millimeter. But let's say, just to be conservative here in our estimate, that we have some overhead of 50% for supporting structures, for dyes, cooling and other stuff, and say that we can fit by 2043, we can fit 16,000 layers of transistors of 1 billion transistors each. Now, that would give us the end of Moore's law for data storing ICs in 2043, and we'll get to a transistor density of 16 trillion transistors in a cubic millimeter, or 16,000 trillion transistors in a cubic centimeter. Now again, I have to repeat how much a trillion is. A trillion is 1,000 billions. So here we have, in a cubic centimeter, by the end of Moore's law for data storing ICs, we have 16,000 trillions that each are, 1,000 billions in just 1 cubic centimeter. That's kind of mind-blowing, at least it is to me. Okay, again, from slide 6 above, that was packed with information. We haven't gotten time at the time to get into all of it, but we take it out bit by bit here in later slides. That slide 6 also showed that we need 2.7 trillion transistors to store 1 terabyte. So a cubic centimeter of data storing ICs in 2043 should be expected to store 6,000 terabytes. Now let me fetch a hard drive here. I have one of these hard drives. You can see it. It's just a small 2.5-inch hard drive here. I have some that have 5 terabits. This is much bigger. There is like 100 cubic centimeters at least in the volume of this hard drive. But in about 20 years, we should be able to get a hard drive that is like 1/100th the size of this one. A small little thing. And it should be able not to store 5 terabytes of data, which is kind of state of the art for physical hard drives today, but 6,000 terabytes. So we will have data storage developed that will far exceed what I can possibly imagine that we will ever need. But of course, we'll figure out ways to use all that space. It's really not a limitation for civilization. Data storage will not be a limitation for civilization to develop to unimaginable levels. Processing power is really where the true limit is. That's what we need more of, but not data storing ICs. They are really good already today, and they will get unfathomable good in the next 20 years. Okay, so I thought it would be interesting to entertain a little bit of comparisons with data storing ICs and stuff we know from everyday life, just to get this into perspective. So say an iPhone 14 today, a typical iPhone will have 1/4 of a terabyte of data storage. So that would be 24,000 times less data storage than should be possible in a new iPhone in 2043 using a 1 cubic centimeter of 1 nanometer data storing ICs. So yeah, we can expect that any storage problems we have today with running out of space on an iPhone, that will be completely in the past in the next few years, because they will store a lot. Also, there has been some studies out there who say that a human brain can store 2.5 petabytes of data. That's 2,500 terabytes of data. That's the number you get when you Google how much data can a human brain store. Now that compares to about 300 years of non-stop video recording with, many frames per second in high detail. And this is why I think that this number here, 2,500 terabits in an average human brain, it's off by 100x. I don't think the human brain can store that much information. And that's from my own experience and just from talking with other people. How much can they remember? I know I remember a whole lot more than other people I meet, but there are a few people who can remember more than me. I don't know if it's just because that the things we talk about is something that interests me and therefore I can remember them. And maybe they can remember a lot of other stuff on something that doesn't interest me, but we don't talk about that and I don't notice. But anyway, I think it's more like 25 terabytes of data that the human brain can actually store, not these 2,500 terabytes. But let's stay with 2,500. That's what you get when you Google it, and say for the sake of the argument that that's true. And even if that's true, it's still less than half of what we will be able to store at the end of Moore's law for data storing ICs, because we can store 6,000 terabytes in a cubic centimeter. We can also say, how big is a human brain? Well, a human brain is 1,200 of these cubic centimeters. So we have to divide by that. And then we get that actually a cubic centimeter of data storage IC can store 3,000 times more than a cubic centimeter of human brain. And my gut feelings say that it's actually 100x like that. So it's 284,000 times more in a cubic centimeter of ICs than in a cubic centimeter of human brain. And then there's the other thing about storing stuff in ICs instead of storing stuff in a brain. An IC stores information with 100% accuracy for decades. Not one bit of information is lost. Not one bit. Whereas brains are grossly erroneous at storing information. You can't remember anything exactly, but you remember stuff approximatively. If you wind the film back, you never see a totally clear image, a video in front of you. You see a really blurred situation. That's what you get. Basically, you are imagining how it looked, and then you kind of fill in the black holes there when you think back of a situation and wants to view that video in your brain. So it's not accurate at all. And also you constantly lose information. Every morning you wake up, you have lost a little bit, you have forgotten a little bit of what you knew before you went to bed. You constantly lose information. You don't do that in an IC, so they're far better than the human brain. Well, to defend the human brain, and that's a big defense of it, the human brain also do computation in the limited space here we have in those 1,200 cubic centimeters of space we have. And really, computation is where the human brain excels. So let's take a little look at that. Okay, I don't know if you're familiar with a guy called Ray Kurzweil. If you're not, look him up on YouTube and start watching some of his videos. He's a very interesting guy. Especially if you, some of the older videos. As of late, he's also an old guy, like he's over 70. The last 3 years he has deteriorated mentally, unfortunately, but he is very sharp. If you go a few years back, listen to those videos. Anyway, in 2009, he made a very interesting presentation, and he estimated that a human brain can do 10 million teraflops. That is 10 million trillion calculations per second. Or 10 exaflops, it's also called. And that's using only 20 watts. That's really what is super impressive here. That's 500,000 teraflops per watt. That's a massive, massive number of calculations. And that is really where you are in awe about the human brain, because we don't have anything like it when we look at our computational ICs. And if you can remember again from this famous slide 6 above, we observed that the state-of-the-art computational ICs in 2022 could do 0.35 teraflops per watt. That's a far cry from the 500,000 that the human brain can do. And also, Moore's law will end for computational ICs in about 2031. With roughly 10x improvement in transistor density, and therefore also the ability to parallel compute. So you can have 10 times more speed. But you know, that will still leave us with only 3.5 teraflops per watt, which is again far below the abilities of a human brain. Then there's another step we can do. We will be able to do another 16x in performance from better computational design. And the reason is that normally when we calculate this teraflops, we've been using a calculation unit that has a lot of precision, and that's needed for doing a lot of different computational tasks. But it's not really high precision is not needed when you do neural networks, which is what all the rage is about in supercomputers now, because neural networks can do AI, and that's where the world of computing is heading. It's not the old world with hard-coded programming. It's, you could call it soft code. AI is kind of soft code, and it's instead of logic statements, it is data that train neural networks and then are able to perform amazing things. Just like the human brains are built. Exactly like the human brains are built. Anyway, so if you only need the smaller precision, that's called a BF16 or CPF8 standard for calculation, then we can do 16x more in terms of flops. And a flop is a floating operatings per second. So multiply again those 3.5 teraflops per watt. Multiply that with 16 and we get 26 teraflops per watt in 2031, and still a far cry from the 500 teraflops per watt for the human brain. I have a few slides here that I like to show you. I have one slide here, slide 20 from Ray Kurzweil's presentation in 2009. He has plotted the power of some supercomputers in terms of teraflops. He doesn't say teraflop, he just denotes them here by the exact numerical number. So he plots that on a graph over time. And as he's famous for doing, he shows there's a linear growth here. And it's a logarithmic scale here, of course. There's one order of magnitude for each step you go up here, so it's logarithmic. And we know when we have a linear line that you can fit on a graph with a logarithmic y-axis, then we know it's exponential growth. So he has been really good at predicting the future using these exponential constant growth that have held up very well. And he's doing it here. He has plotted in the human brain here. That's the computational speed required for human brain functional simulation. That's 10 to the 16. Now, the estimate I have used by Ray Kurzweil is computational speed required for human brain neural simulation for uploading. So you could basically simulate completely in every detail a human brain and its functioning. That's the speed I've used. That's 10 to the 19s. That are those 10 exaflops. That is 10 to the 19s floating operations per second. And he also plotted when he thought the first exaflop supercomputer would be created. And he did that in 2009. And he said that would be around 2019. I happen to know, now we are in the future here, his future. So it has happened. We actually got the first exaflop computer with 1 exaflop this year. So it was not as early as Ray Kurzweil predicted, but close enough to say that his predictions hold true. There is an exaflop computer in existence, but it's only 1.1 and it's only recently made. I'll tell you about another supercomputer here in my next slide, and that's the one that Tesla is developing by Elon Musk called the Dojo project at Tesla. They are developing a supercomputer and they're building everything around that supercomputer, including the chip that it runs on. So they don't use NVIDIA's chip, they use their own chip that they have developed. It's called the D1 chip. It's not state-of-the-art nanometer technology. It was built on 7 nanometer technology. So it has a way to go to get to 1 nanometer. But I'm just going to tell you this about this supercomputer because it's probably become the world's best known supercomputer. Everybody are talking about Tesla, so it's more intuitive to relate to something that you already know. So that's why I'm using this computer. So they have this D1 chip they developed that has 362 teraflops of speed using this BF16 standard. And they put that chip into a training tile, so they can fit 25 of those into a training tile. And then they get 6 petaflops. And then they stack these training tiles into cabinets or racks. And then they tie more of these racks together to form a supercomputer here that achieves 1.1 exaflop in speed. But the thing is, they have built the chip and they have built the tiles and they also built the cabinets that contain these tiles. So I don't remember exactly how many tiles they can stack in a cabinet. But they haven't built the actual supercomputer yet. They haven't stacked all these racks together to form this 1.1. But the whole system has been designed so that should be possible. And I do believe they said that they'll be ready to fire this stuff up in first quarter of next year. That's in not that many months from now on. I do believe they will be able to do it. They had a technical problem, of course. It's the first time Tesla does this ever. So this is their first attempt at making a supercomputer from scratch. So of course they had technical problems. I don't want to go into the details of these technical problems, but they have solved them. And there was some problem with this D1 chip that needed modifications in order to actually work and not crash all the time. But I think they have solved them and they will be able to boot up this supercomputer with 1.1 exaflops. So it will be among the 5 fastest computers when it boots up in the world. And we know Tesla, they are relentless, and I do believe that they are a company to follow to see who will have the fastest supercomputer in the world. But let's take a look at what this one can do and how much watt and energy it uses. It's actually not that impressive if we compare it to a human brain. So this Tesla Dojo supercomputer has 1.1 exaflops. And in teraflops, that is 1.1 million teraflops. And the power consumption of a D1 chip is 400 watt. I estimate there must be some overhead for cooling and other stuff when you pack it all together and it needs to be cooled and all kind of communication needs to happen, so you need more energy use for that to facilitate communication between these chips. And then they pack, in this supercomputer, they managed to combine the compute power of 3,000 of these D1 chips to get that exaflop. So the total power of that is just 400 times 2 times 3,000. That's 2.4 million watt it uses. If you divide that, the watt usage, with the number of teraflops that this computer has, 1.1 million, you get only 0.5 teraflops per watt. That's kind of disappointing. You know, the average human brain has 1,000,000 times more efficiency in terms of compute than this supercomputer. It was 500,000 teraflops that was estimated per watt, according to that estimate there by Ray Kurzweil. I have also researched how other estimates of the brain, and they vary wildly. You know, some are many orders of magnitude higher than those 500,000, and some are many orders of magnitude less. So it's really not something that there's anything scientific consensus about. But I've taken this estimate by Ray Kurzweil because I know this person. I know he's a brainy guy. He is well known for spending most of his life thinking about these problems. So I have most credibility in him because I've seen what he's done. And I haven't seen, I don't know, these other researchers. I don't know if they're any good or what they are. But I know this guy here. I think he is the real stuff. But he could still be far off by a couple of orders of magnitude. That's for sure, because it's such a difficult area to estimate the speed of a human brain. Okay, but anyway, and we also saw here that the estimated teraflops in watt at the end of Moore's law for computational ICs in 2031, that would be about 56. That's still 4 orders of magnitude less than a human brain per watt in efficiency, which is really disappointing. To be honest, it's, to me at least, it's disappointing that it looks like we are running out of computational efficiency speed for electronic internal circuits in 31 at a level much below what's possible in a human brain. However, in a few slides, I'll just explain that there are actually hope. There are way out of this, but I'll come back to that. So what kind of alternatives do we have to progress the efficiency of computation rather than these electronic internal circuits? There is one alternative, and it's computational circuits. It's an obvious alternative to use such circuits because they use photons instead of electrons. And photons, they need less energy than electrons to be moved around. And secondly, they move faster than electrons. And third, which is perhaps even the most important thing, is that they can apply numerous of wavelengths simultaneously for each optical transistor, thereby doing the work of multiple transistors in a single optical transistor. And since there are billions of wavelengths, the potential is that you could get billions of calculations simultaneously in using an optical transistor rather than an electronic transistor that uses electrons. But I definitely believe that there are orders of magnitudes to be gained in terms of computational efficiency with the optical ICs rather than electronic ICs. And we also need that because, as we just saw, we need a 10,000x improvement over what we can expect to be able to do with electronic internal circuits at the end of Moore's law. That's needed, or we won't be able to beat the human brain in efficiency. Okay, this is just some sources for the past 5 slides I've gone through. I have a final observation to make, and that is that a 10x improvement might actually be doable beyond what we have talked about in the previous slides. So Moore's law might not be completely dead after the dates I just mentioned. And to see that, we should note here that an integrated circuit that packs 1 billion transistors per square millimeter using 1 nanometer tech, that will have an average area for each transistor of 31.6 nanometer times another 31.6 nanometer, where you can fit in 1001 squared nanometers. So why does one transistor need 1001 nanometer squared if you can build it using 1 nanometer tech? It does so because a transistor is actually a little machine that is built up of several smaller components, each that can contain nanometer scale features. And that's one explanation. So it's a complex little thing that require many features that might need to be built on the 1 nanometer scale. And the other reason is that transistors is not all there is in an integrated circuit, although it's the most frequent component there is. There are also other components like resistors, capacitors, diodes, and other stuff. And then of course all the wires needed to connect them. And all that needs to be fitted into this area of 1000 nanometer squares. And that's why. So my point is, it could be that there are more brilliant IC designs that will enable us to pack even more components into an integrated circuits using the same 1 nanometer technology that should be available in 2031, at least for computational transistors, and then again in 2043 for data storing transistors. So one could perhaps think that there is a further 10x improvement of transistor density, so that we on average would use 10 nanometer times 10 nanometer, or a total area of 101 square nanometers are needed per transistor. That would also give us 10 billion transistors per square millimeter, or it would give us 1,581 trillion transistors per cubic millimeter for data storing ICs. But that would, in my opinion, be the absolute end for Moore's law. I think we will end up with a reality that says Moore's law will end somewhere between 1 billion and 10 billion transistors for computational ICs, and it will end up between 16 trillion and 1,600 trillion transistors per square millimeter for the data storing kind of ICs. And then, of course, if it is possible to go beyond 1 billion transistors per square millimeter and 16 trillion transistors per cubic millimeter, if that's the case, then also I believe some more years are needed beyond those end dates I have estimated above. That was 2031 and 2043. Okay, so now we have finally reached the conclusions of this presentation here. It's been argued that Moore's law will end in 2031 with regard to the computational and electronic ICs using 1 nanometer tech. Such ICs should be able to have about 1 billion transistors per square millimeter with a compute efficiency of 56 teraflops per watt using this BF16 methodology. And this is 10 times better transistor density and 10x to 160x better compute efficiency as measured from the best computational ICs anno this year, 2022, using this FP32 standard. And this presentation has also argued that Moore's law will end in 2043 with regard to the data storing ICs using 1 nanometer fabrication tech as well for these ICs. And such ICs will have a transistor density of about 16 trillion transistors per cubic millimeter, and 1 cubic centimeter of data storing ICs in 2043 should be expected to store almost 6,000 terabytes. So a lot more than the hard drives we can buy today that max out at 5 terabytes and that are a lot bigger than 1 cubic centimeter. They are like 100 or 120 cubic centimeter large and can only store 5 terabytes. It has further been argued that there is a potential for an additional 10x improvement in denser integrated circuit component design at the 1 nanometer level. So up to 10 billion transistors per square millimeter should be doable if that is possible. But I think Moore's law will end somewhere between 1 billion transistors and 10 billion per square millimeter for computational ICs. And for data storage, that would imply a 100x increase, or 1,600 trillion transistors per square millimeter. Okay, I do not know of any better future technology that is emerging for data storing after the electronic data storing ICs max out in 2043. However, I think it's obvious from first principle thinking that computational electronic ICs will be superseded by optical ICs that has the potential to be many orders of magnitude more compute efficient than computational electronic ICs. Also, I don't believe that the human brain, who's biological, is actually able to compute more efficiently than something we can make artificially in a factory in the future. I just don't believe it. I think we will be able to manufacture artificially stuff that is way more efficient than the human brain, because I don't think the human brain can be as efficiently organized, because it is biological, as we can in a factory that goes to the very border of physical limits of nature. And then there's, of course, some people who have been following this presentation through the end here would have thought, why doesn't he talk about quantum computers? Because people are talking about quantum computers. And I'll then mention it here in my conclusion. Well, quantum computers is a possibility to create ultra-fast computers that exploits quantum superpositions of particles to create quantum bits that can have states of 0, 1, or something in between. And that's a quantum bit, and then they use that to generate ultra-fast computation. To be honest, I don't know exactly how this functions. It's beyond me, but I haven't invested that much time in it. And the reason I haven't invested much time in it is because I have not seen any quantum computer that are able to solve any real-world practical compute problems. They are all very academic, the problems they solve, and they have no practical applications. And until they have a quantum computer in operation that can actually solve a real-world problem, I'm not going to be too much interested in it. It could be that they have these fantastic machines, but they cannot calculate anything that's useful in the real world. And then they will not mean anything. Then they would only have been an academic experiment that kind of faded out in nothing useful. But I think they will eventually. Someday someone will have a computer that actually works and that can solve real-world problems, and that also can function at temperatures that are not close to the absolute 0 point at 0 Kelvin, which most quantum computers today need to operate at, which makes them very unpractical. However, I do believe that optical ICs has a future, also because they're already in production, and some supercomputers in the world are made using optical ICs to do the computation. So I think they have a great future. But I haven't talked so much about them here. I only briefly mentioned them. And that's because I think it's a whole nother presentation and another video. I do want to make a video about optical ICs, because I think it's fundamental that we progress computation beyond what is possible with electronic computational ICs that cannot beat the human brain apparently in computational efficiency. So that we need in order to make a future where we can create artificial self-conscious beings that are not any larger than us. So we could create robots that are like us and be superhuman, both in terms of thinking and abilities. Maybe that's the future of humanity, that we convert into machines that are just much better than our biological self at the current state. But okay, that will be another video or a couple of other videos in the future. And I hope you liked this video. It took me some time to prepare and also to record. So I hope you subscribe. I'll do more videos and we'll have the level that you see in this video. And since this is only my second video in this channel, I do expect I'll get better at communicating and also better at making these presentations. So thank you very much for listening here to the end of this video. It's been fun making it for me, so I hope you had fun watching it. Thank you very much.